If you are new to astrophysics or cosmology, you should be aware that now is a wonderful time for missions and discoveries. Every mission and technology was created with the intention of providing us with a brand new understanding of the cosmos. This includes analyzing fresh data, discovering new universes, and updating outdated hypotheses. Throughout all of human history, there has never been a time when science has flourished more. We have never experienced such a massive amount of discoveries every single day. Just look at the papers. Hundreds of papers are published every day on the most fascinating and diverse subjects, including the search for exoplanets, the merging of black holes, the detection of gravitational waves, and perhaps new cosmological studies that will provide us with a more precise estimate of the Hubble constant. Every day brings a fresh discovery, and because we learn more about the cosmos every day, we also grow to know ourselves better. All of this relates to contemporary astrophysics, but today we want to return to, say, a classical question because grasping the larger, more fundamental picture is necessary for gaining a thorough understanding of the universe. If you approach a Monet picture too closely, all you can see are the dots. You must step back and view the artwork from a different angle in order to fully appreciate it. That is when cosmology comes into play. In this video, we'll discuss what might transpire if the universe had a major crunch, both for time and for ourselves. We are aware that everything began with the Big Bang, that the universe then expanded and is still expanding right now, and that the pace of expansion will likely vary and slow down over time, eventually leading to the so-called Big Crunch. Yet, at first, this came as a surprise. Albert Einstein and other scientists believed for a very long time that the universe was static and unending. In reality, observations throughout the years have revealed that it is really expanding more quickly. This implies that time does indeed have a beginning and that it must have come from a more compact condition known as the Big Bang. And it probably has a conclusion. Although theoretical physicists are unsure of how the universe will end, one hypothesis is that it will squeeze and contract, growing smaller and hotter as it does so. The huge crunch is the name of this end. Exactly how do we get there? What are the results of it? Here's basically what we do know. The renowned Friedmann equations were derived in 1922 by Russian physicist and mathematician Alexander Friedmann. These calculations demonstrated that our universe might grow or contract rather than remain in a stable state, and that its fate was dictated by its density. If there was enough stuff, gravity would eventually stop the universe from expanding and bring it crashing back inward. As astronomers totaled up all the stuff in the known universe in the 1960s and 1970s, they came to the conclusion that there was enough mass for the universe to eventually collapse into an indefinitely dense state, or possibly even a massive black hole. Some believe that the universe will begin yet another expansion, known as the Big Bounce, after being squeezed into an impossibly small point, or the Great Crunch. A notable advocate of the Great Crunch during the 1970s and 1980s was physicist John Wheeler, who was credited with helping to develop the phrase black hole. It was an apparent outcome to him. Wheeler believed that each black hole served as an experimental model of the final condition of the cosmos at the time of the black hole revolution. Galaxies colliding and extremely chaotic star-to-star interactions are predicted during the Big Crunch. The universe will become incredibly chaotic on long periods if a massive crunch occurs. If only life existed elsewhere in the cosmos, this would mean the gradual extinction and purging of life as we know it everywhere. We require one primary component in order to reach the crunch. It relates to matter. If for some reason matter in the universe reaches a point where it starts to shrink over time, rather than expanding indefinitely, gravity may then take over as the dominant force. The universe would effectively collapse in on itself at that point because to the gravitational attraction, which would also cause the universe to contract and bring about the collision of stars, planets, and entire galaxies. Simply put, Everything will implode back into a singularity if the expansion of the universe slows to a crawl and the Big Bang occurs in reverse. At first, physicists thought that the loss of matter with time was the only factor dictating the course of the cosmos. But they soon realized their mistake. That body will eventually give in and fall back down for as long as there is no additional force pulling it up, much like anyone who defies gravity, such as when you toss something up. Consequently, it previously appeared plausible to anticipate that gravitational forces would ultimately prevail. Yet that was before researchers found that the universe was indeed speeding up in the most distant places. Scientists had to presume the existence of an unidentified substance they called dark energy in order to explain this occurrence. The general consensus is that this object is causing all galaxies to move farther apart. There seems to be little room for the idea of a great crunch with dark energy, and what little is known about it. As of right now, observations by NASA's Chandra X-ray Observatory show that the university's dark energy level is stable. Just for clarification, a Big Rip, another universe-ending scenario that predicted everything, including atoms, to be torn apart, would have been supported by an increasing dark energy strength. The most plausible scenario is still an expanding universe, even with a constant level of dark energy. The Great Crunch will have to remain a less popular explanation unless data is gathered that contradicts these qualities. But what if fresh research revealed that the Great Crunch will indeed be the end of the universe? Considerably better to be ready for it, wouldn't you say? What should we anticipate from it? For instance, we can consider the Big Bang to be the same process as the Big Crunch, except temporally reversed, if the universe shrinks and ends in a singularity. Let me elaborate more. Everything begins to expand after the Big Bang, reaching the point where we are now. If we could go back in time and watch the universe's history as a movie, we would start at the present and wind up back at the Big Bang singularity. Hence, it's not so strange to believe that time will travel backward if the universe begins to contract as we approach the Big Crunch. Is it? Let me introduce you to an old acquaintance named entropy who can help you with this question. Entropy is a measure of the energy in a system or process that cannot be used for work in physics. It is frequently related to a thermodynamic system's condition of disorder, randomness, or uncertainty. The universal entropy is always rising, according to one of the most fundamental laws of physics. Entropy will be monitoring you, and it will grow with every process that takes place in an isolating system, every breath you breathe, and every move you make. There always seems to be a confluence of events as we move forward in time. In the universe, objects travel in direct proportion to their speed. Due to the influences of gravity and other factors, they alter their motion. The cosmos is expanding at very massive sizes. Also, the entropy of the universe is increasing everywhere we turn. We believe that all of these things will continue as the story of our cosmic evolution unfolds. The universe will continue to expand due to dark energy, the laws of physics will continue to be followed, and the laws of thermodynamics will still be in effect. Even though there is yet no proof, some scientists believe that the arrows of time and thermodynamics may be connected. Dark energy may also change over time rather than remaining constant, according to certain theories, which leaves up the prospect that it could one day work against and stop the expansion of our universe. Together, these two premises allow us to ask, would time travel backward if the universe were to shrink in size and experience a massive crunch? If so, would entropy decrease? Let's see what the science of physics has to say about it. Time reversal symmetry is one of the most significant symmetries in all of physics. Simply put, it asserts that whether the clock is running forward or backward, the principles of physics apply. There are numerous instances where a phenomenon that occurs when the clock is running forward corresponds to a phenomenon that occurs when the clock is running backward in every case. For instance, if you run the clock both forward and backward, two billiard balls colliding will react precisely the same, right down to the speed and angle that the balls will shoot off. In the quantum realm, this isn't always the case, but that's a story for another clip. The time reverse is symmetrical if we ignore this minor point, but it doesn't seem to be the case for all of the phenomena we observe in the macroscopic world. Certain events unmistakably show a temporal arrow or a bias for a specific one-way orientation. You won't ever witness the pieces of glass spontaneously reassemble themselves if you go to your kitchen, take a good glass of red wine, and then slam it against the floor. Consequently, it is obvious that there is a preferred path for things to take, an arrow in which things flow. The rules of thermodynamics, on the other hand, essentially indicate that there are a finite number of conceivable arrangements for the particles in your system, and that as time passes, all systems will trend towards the configurations that contain the greatest number of configurations. Some researchers believe the relationship between the time arrow and the thermodynamic arrow can be found somewhere in what we just discussed. In other words, according to physicists, there is both a perceptual and a thermodynamic arrow of time, both of which always point in the direction of progress. Nonetheless, the observed arrow of time appears to be essentially unaffected by what entropy or thermodynamics may do. It seems like you really like this video. If you're still here, then why you don't press the alert bell? Will entropy fall if the cosmos begins to shrink? No, is the response. Remember that the entropy of the universe is already increasing due to processes like particle collisions, the exchange of angular momentum between planets, stars, and galaxies, and others. In order to comprehend this, entropy would rise as well if the universe shrank, since the same processes would continue to take place, possibly more quickly. In a nutshell, everything that increases entropy now will continue to do so in a universe that is contracting. Hence, even if the cosmos shrinks, entropy will still increase. We can confidently assert that time would continue to flow in the same direction, since a rise in entropy is connected with a forward thermodynamic arrow, which is ultimately associated with a forward time arrow. This situation is intriguing because, in accordance with Einstein's general theory of relativity, clocks function differently under intense gravitational fields, such as those found near black holes. We would inevitably find ourselves at the edge of a black hole if the universe were to collapse and approach a big crunch, and as we did, time would start to stretch for us. What a pleasant way to go. Here's where the video ends. Thank you for viewing. Be sure to like the video and, if possible, enable notifications.